some data sets with different component classes. They used the neural net YOLO V11 for instance segmentation. They're also doing some classification. They were training it to do some better classification. Got the results of 91% mean average precision. Shows, and they'll show a robot that was actually using the vision to go over. So back on, the team placed second place in the engineering category at the Synopsis Science Fair. Vignesh has interest in computer vision, robotics, and AI. He's on the school's FRC robotics team. He has experience in TypeScript, React, and SQL. Laylet specializes in computer vision, robotics, and embedded systems, Arduino, Raspberry Pi, YOLO V11 object detection. He's a lead programmer on the VEX robotics team, co-president of the Data Science Club. Cool. Let's see. And then the next, working at the UC Santa Cruz's CMOS program for photonics and solar cells, developed the CAR-T cell therapy manufacturing QC system for the HSEC bioengineering competition, where he placed first. So please help me give a warm round of applause to our speakers.
Our project is a low-cost automated approach to e-waste sorting. So nearly 62 million tons of e-waste is produced every year, and it's one of the fastest growing streams of waste in the world. For context, this amount is 6 times the weight of every commercial airliner ever built. And the key issue is that less than 20% of this e-waste is formally recycled. So a large majority of it is either landfilled or it's exported to third world countries where it's treated like very poorly. So it's usually poor workers in poor working conditions who are working with this waste, or it's burned in informal yards, which creates even more pollution. So inside each pile of e-waste and each PCB, there are billions of functional components that are recycled. So this ranges from capacitors or cheaper transistors, or it could also be more expensive integrated circuits that are being recycled here. And each PCB individually carries dozens of parts that also work, and they all survive when they're put to be recycled, but destroyed in that process and scrapped to become materials. So even if they survive, they're completely scrapped, and that destroys any capability. And that destroys any capability of them actually being utilized again. So this is the question we set out to answer. If these large-scale businesses have the capability, and for them it's more profitable to like completely scrap these components, is there any accessible point for smaller businesses or smaller shops to get into e-waste recycling? Because it's not really a cost-effective approach for them at that low level. So we wanted to target that demographic and see if we could preserve components on PCBs and help them be recycled more effectively.
So when we first developed this project, our initial constraint was cost, and we set out to create a system that wouldn't compete with bigger businesses who had large industrial mechanisms who could destroy parts in bulk for profit, but rather be geared towards small businesses who operate at a smaller scale and can actually profit from preserving these key ICs that would be destroyed in a large industrial tumbler machine. And our hard ceiling from day one was under $1,000 to achieve this goal. And that target shaped every choice we made, from using a pre-owned printer instead of a custom gantry system, a consumer webcam instead of machine vision, and older or used components rather than newer components that would be a later model. And we ended up at $345, which is roughly a third of the budget.
So now that we have the budget in mind, let's talk about some of the current solutions to this problem. When we looked at the existing landscape, we found 2 main methods of how you can recycle e-waste how you can recycle e-waste. So the two ways are through industrial tumblers and repurposed pick and place machines. So let's talk about the industrial tumblers first. So these tumblers are essentially large drums where you can place e-waste like PCBs, and they spin at an extremely fast speed and are also heated up. So in this process, all the components from the PCB and the boards itself are essentially lost, they're destroyed, and you can't harvest them for future component recovery. The second type of method that we saw was through repurposing pick and place machines. So what pick and place machines are that they are essentially machines that construct the PCBs. They're inherently not meant to disassemble the PCBs, but rather are meant to build them through pre-made manufacturing files. So this was also not such a viable solution, number one, because of the massive cost associated with it. The cost for this usually varies around $20,000 to $50,000, which is extremely out of our budget and out of budget for many small businesses that should harvest components like this. In addition to the cost itself, there was also a big factor associated with the repurposing the machine. In order to repurpose the machine to disassemble parts, you'll need to add a heating bed, a vision sensor to identify components for multiple parts, for multiple different types of PCBs, and you'll also need a different specialized vacuum nozzle to accurately pick and place, to accurately remove the components that you want. So in addition to the cost, all of these factors make the pick and place machine not the most viable solution as well. Another way is through manual sorting. So manual sorting is the use of human labor, which is obviously much more inefficient for businesses than these advanced machines. Although component recovery is able to be preserved, it's extremely inefficient for these businesses. So below $1,000, as you can see, none of these solutions really exist for component harvesting. And that was a gap that we wanted to build into. So let me run through a system overview first. So our system overall is constructed of 5 major subsystems: the gantry, so the motion system, the tool head, which picks up the parts, the computer vision system, the heating system, and the control system. So the first part of the subsystem is the gantry. As you can see, we're using a repurposed 3D printer. That 3D printer is actually a CR10S. So it's a relatively old 3D printer, and its motion capabilities aren't that great. But some of the reasons we picked it are it was very low cost. And another benefit of it was its print area was larger. So we had the ability to place boxes on the, as you'll see later, we had the ability to place boxes on the print bed where the parts could be sorted. But in the future, a print bed of this size isn't specifically necessary. So next, for the tool head, we utilized a vacuum nozzle system, and then we had a BL touch probe on a stepper motor driven system, and this was essentially just used to pick up the parts, detect their heights, and then sort them effectively. Next, you have the key part of the system, which is the vision system. And this uses a YOLO V11 instant segmentation model with 19 part classes. So 19 classes for each individual component to be sorted into. And this system runs from the camera at the top of the printer, as you can see there, and looks down on the PCB and identifies components and tells the system where to move. Then you have the heating system. So obviously, to get components off of a PCB, you need to melt the solder on them. So that's what this system does before the parts are actually removed. Then the control system. So as I mentioned before, this is an extremely old printer. Newer printers have shifted to this software, but older printers typically run on a Marlin software, which is closed source and pretty slow and inefficient. So we needed to switch to a software called Clipper, so you connect a Raspberry Pi to the 3D printer, and you run Clipper off of that because typical 3D printer boards do not have the ability to run Clipper. So the Raspberry Pi treats the board on the 3D printer as a slave board of sorts. So you run Clipper on that, and that allows you to directly connect to your computer and control the motion via code. So that allowed us to tie in our computer vision to the rest of the system. Yeah. So the toolhead had 3 major iterations. This was a pretty major engineering task. So we had a few constraints at the start. So at the beginning, we wanted to use 3 specific tools. So the tools we wanted to use were a gripper, firstly, to pick up irregularly shaped PCB parts. So that could range from inductors to weirdly shaped capacitors to connectors, things like that. And then to pick up the flat ICs or any component with a flat top, really, we wanted to use a vacuum nozzle, which is often used in pick and place machines. And as we found out, it works quite well for the task. And then we needed a way to measure the height of each component because the computer vision system only gives us X and Y coordinates. So we needed a way to get Z coordinates. So with these 3 tools, an issue we ran into was the fact that if you kept all 3 tools at the same height, when the gantry moves down onto the PCB and tries to pick up a component, there's a chance that a part next to the part we're trying to pick up is taller than the component we're actually reaching for, which would mean if the tools are like all side by side, then one of them could ram into one of the parts that we're not focusing on. So to work around this, our initial idea was to use a hinge system. So as you can see in the first image, I thought of 3D printing a hinge and then connecting a servo motor to the hinge. So we would have the gripper and the vacuum system on 2 hinges, and then the sensor would just stay in place. So you can move them whenever needed and whenever one of them was being used. So one of them was always at a lower height than the other 2. The issue with this system was that the hinge and the servo motor system was extremely bulky, and
Oh, still pretty loud.
the cheap servo motors we were using were also pretty weak for the task, and we wanted to upgrade to stronger servo motors that would make it even more bulky. And then the sensor we used to detect height for this initial system was called an FSR force sensor. The issue with this was it gave inconsistent readings of height because it was mainly supposed to be used for normal touch, not specifically sensing on like a thinner plane. So our second idea to move from this was a dual rail system. This dual rail system mounted the sensor in one place, then utilized a servo motor to move a rack and pinion gear system, as you see in the second image. So when the sensor was being used, both of the rails would be in their middle position. So the sensor was lower and it could be used. And then when one of the tools was in use, we would lower it down. So we would have a good amount of distance between itself, the sensor, and the other tool. And then when the other tool was in use, we just lower that down. So the idea with the system was good, but the implementation was still not there because the system still used a servo motor. And the issue with this servo motor was that, so usually servo motors, they have like a 180 degree area of range of rotation. But to move the rails this distance, we needed more than that. But a 360 degree continuous servo has no reference of position on itself. So it doesn't know where the middle position is. It doesn't know where the farthest end is. So that could easily cause issue for us. And then for the sensor on the system, since we couldn't use the FSR sensor, we wanted to try to repurpose a keyboard switch on it, but that didn't turn out well as well because the frame we placed the keyboard switch in kept moving, so it was like an inconsistent mounting system. So our final prototype utilized the rail system, but what it also did was it switched to a stepper motor, which has the ability to track its position. So it knows when it's at the furthest end or the other furthest end or at the middle position. And then it switched the sensor system to a BL touch sensor. And this sensor is typically used on 3D printer bed leveling. The reason we picked this,
Hold it in front of your chest.
oh yeah,
Film is using that feature of moving the background and
Oh.
your device is in the background. So if you put chest behind it,
okay.
it doesn't get blocked.
So this is a BL touch sensor. So it's typically used on 3D printer bed leveling, and it's extremely consistent in height detection because that's its sole purpose. So it goes down to each part and detects the height like that. And then for the rest of the system, we're using a normal like 6-volt vacuum pump for the vacuum nozzle over here. And then for the electronics on this, it uses a simple Arduino Nano, which is connected to a H-bridge driver for the motor, and then a TMC stepper driver for the stepper motor. And then in the actual overall system, it's just tied to a power supply, which connects to it while it moves. So yeah, oh yeah, and then the sensors that we go, I already went through some of them, but just to like cap it off. So we started off with the force sensitive resistor, the FSR sensor, and that gave us inconsistent thresholds. It went off at different times, which would mean it would detect at different heights. Then another sensor we tried in between iterations was a capacitive proximity sensor. We tried the sensor because we wanted to try a methodology that didn't directly touch components because we thought that would be better overall. The issue with this was finding a capacitive proximity sensor thin enough to not hit other components when it moved down proved to be like very difficult. And the only model we could find was extremely old and gave inconsistent like sensor readings. So it was like too noisy. Then we thought of using a laser distance sensor, but this was just too expensive and too bulky for our like cost and our physical dimensions. Then the keyboard switch, which lacked precision. And finally, we landed on this BL touch probe.
So the second major subsystem of our project was
Move the microphone.
Yeah. the second major subsystem of our project was the computer vision system. And this was essentially the system that made the whole like big part of what made the project work. So the goal of the system is to look at a PCB using the camera that we have on the top of this of the printer there, and it needs to look at that PCB and create annotations on the individual components of where the position is so that the printer can accurately move to and pick up those components later on. So the 3 stages we had were detect. So a YOLO V11 neural net, a large segmentation model, outputs pixel space masks across 19 different component categories. Then it maps using a 3rd-degree polynomial fit on 20 different reference points, using which converts pixel coordinates that the machine learning model outputs to printer millimeters. And then finally, the last stage is to probe, which where the BL touch contacts the part to measure the height. And the 2D model can't tell how tall something is, and the PCBs are not flat, so it needs to know where the component is spatially in the 3rd dimension. And then only after all 3 stages of the vacuum descend and actually pick up the part. The reason why we used YOLO V11 instead of any other model was that the system is able to create a mask around the image and not just a simple rectangular annotation. And that's useful because every part is not uniformly rectangular across all the component categories. So if the center of a certain square or rectangular part was or not square or not rectangular part was not on the actual component, that would be an issue for us. So the mask can cover all types of shapes of components. And the output of the model is a list of class, mask, polygon, and confidence tuples. And the class is the type of component. The mask is obviously the outline of where the component is on the board, and a confidence score, which tells you how confident the machine learning model is that a certain component is that component. And the workflow code in our main.py reads these detections, splits them by type into capacitors, ICs, or integrated circuits, and other components, and passes these pixel centroids to the coordinate mapper. And then we have bins around the PCB, which are labeled with specific components that the machine picks up and subsequently places into each bin. The next part was building the data set for the machine model to train on. So there were 3 public PCB datasets which we used, and none of these PCB datasets agreed on annotation type, in the image size or lighting or class names. And there were many issues with fitting the different types of data to the model, which could be accurately interpreted by it. So we used a class map, which normalized each of the class names and made it so that the machine model could take like different types from different data sets and combine them together. So we had in a data set called FPIC, which we used, the capitalization differed in every single one. So it from another data set called PCB component in Ninja and WACV in the other data set, what they all had different types of capitalization. So we needed to combine those into a unified class map, which could accurately combine like the same component type, but different names in the data sets. So the way we did that was the class map handles 3 separate annotation formats. FPIC and Dataset Ninja use supervisedly JSON with per object geometry, so bitmaps, polygons, and rectangles, and WACV 2019 uses XML with bounding boxes only. The conversion script decodes each format separately into a normalized YOLO segmentation polygon coordinates, and the model is able to use that to train and recognize on in the future. The class unification was the hardest engineering problem. The 3 datasets independently labeled their own names for the same components. So FPIC called SMD capacitors C, Dataset Ninja called them cap1 through cap4, and WACV called them capacitor. So the merge map in the final collab pipeline has 48 original labels collapsing into 19 canonical classes. The class collision bug to put that in more detail, the dataset Ninja's cap1 through cap4 were initially mapped to SMD capacitor during debugging, but the primary pipeline correctly maps them to electrolytic capacitor, which was an issue that we had throughout. The dataset sizes after finally combining and oversampling, and oversampling is just to like artificially increase the number of certain components so that we can detect them better in the actual pipeline. So since we were mainly detecting large components only because our hardware was only suited to, and our goal was to mainly get large components, we need to artificially oversample the large components in each of the data sets so that it would more accurately train on those types. So we had 8,976 images with 40,000 object instances across 19 different classes. So in the general overall structure of our vision training was that we initially tried DETR, which was the most accurate architecture we tested, but too slow to train and use. And the YOLO neural net that we eventually ended up using was more efficient and took less time to train than DETR. So we used that in order to speed up our iteration process for improving the model and also to reduce the amount of time it took for the processing to happen on our computers during the actual running of the pipeline. We landed on YOLO V11 large segmentation, which was a small accuracy hit versus DETR, but roughly 3 percentage points on box mean average precision, but ran much faster and was easier to train. So we were able to ship our model much faster and finish our project faster in time for the Synopsys Science Fair. Our final setup was the Colab A100 GPU with a 640 pixel image size at 100 epochs, validated on a 100 by 100 millimeter test board. Our headline numbers were 86.1% box mean average precision at 0.5 area covering the board, and 84.9 mask mean average precision, and 78.9% on an actual PCB that we did in our actual pipe. Our model was strongest on integrated circuits, electrolytic capacitors, transistors, and connectors. And this was actually better for us because our model was initial goal was to detect larger components, and that vision system only being better at detecting large components was not a bottleneck to solving our final goal.
Just for the audience to understand, the pink areas on the right side image, that's what the neural net was detecting. Classified into 1 of 19 types of pieces of electronics. And then the blue text is the labels of those 19 different classes. So it's a little bit busy, but the computer would understand it to figure out what to how they're looking at.
Yeah. So until now, Vignesh was explaining how we detected each component, from using the computer vision model. So now, after we detect each component, we also need to convert that into the printer coordinates, because it's not enough if we just get the centroid of the bounding box, but we also need to actually act upon it. So our first try in converting from pixel coordinates to printer coordinates was using homography. So this is basically mapping a flat surface in pixel space, which is what the camera sees, to real world coordinates in the 3D on the 3D printer. So for our use case, this did not work at all because of the lens distortion in the camera that we chose. The camera that we chose was a 4K Acer camera. This is not specifically meant for such kind of heavy computer vision tasks, and we didn't use like a specialized camera for that due to minimizing costs. So we found an alternative way to make this possible. So what we did was, instead of correcting for the distortion that we would see in the camera, we directly fit a third-degree polynomial onto the PCB on the printer bed. So essentially, the polynomial simply absorbs the distortion and accounts for this distortion when calculating the printer coordinates. So there was no separate undistortion step that had to be first done before actually printing out the 3D printer coordinates. So the result for after implementing the polynomial fit was we had a 0.89 millimeter accuracy across the 100 by 100 millimeter test area. So that was extremely good because it stayed within our 2 millimeter pickup tolerance for the vacuum nozzle. To implement the polynomial fit, we also had 20 calibration points, as you can see. So we manually plotted out 20 different points. Yes. So we wanted to account for the lens distortion instead of having a separate step to undistort the camera. So this step was just done on the printer bed because that's where all the action will be happening. Yeah. Yeah. So obviously a key part of our system is actually desoldering the PCB and melting the solder around the parts, so the parts can actually be picked up. And unfortunately, this wasn't as simple as it may have seemed. So we're using a commercial reflow plate. And the issue with using this initially is reflow plates are typically used for SMD PCBs. So when you're like soldering an SMD component to a PCB or removing it, it's not typically used for through-hole components, which have parts or points coming out the other side of the PCB. And the issue this gives rise to is if you put like, right here we have like an Arduino. If you just put an Arduino on it, the points at the bottom of the PCB cause heat not to spread evenly to each part. And that means desoldering takes a lot of time, or on some places it doesn't happen at all because like as you see the big connector at that end, it has bigger points sticking out of the bottom of the PCB than the other areas, which means it lifts up that area more, and the parts around that area don't get desoldered as fast or like at all. So what I found out from doing a bit of research is that some in some places they use sand bats to desolder PCBs. So instead of using sand, I thought we could use a similar crystalline substance. And after some testing, realized that normal table salt conducted heat extremely well and worked very well for this task. So as you can see right there, that's just table salt on the heating plate. And once you place the Arduino on it and leveled it, the heating became extremely effective and it was able to melt the solder in like a few minutes. So another thing we had to think about when heating is that PCBs can't sustain that much heat for a long period of time. Like according to JEDC standards, if you the JEDC peak is 240 degrees Celsius for under 60 seconds. And 60 seconds, even though it's not too little time, typically you want like more room to have time to pick up the components before you're putting your components at risk, because obviously the entire goal is to preserve working components. So what we realized is we could heat up the PCB to about 240 degrees Celsius initially until the solder melts quickly, and then we can lower it back down to around 210 to 200 degrees Celsius to sustain that temperature, and the solder would stay melted for that time period and wouldn't be harmed as quickly, so we would have more time to remove the parts. And right here, right now it's a very basic system. So we just have Kapton tape around it, and in the train and what in actual use, we have Kapton tape holding the PCB down, but later we want to add like proper clamps and design a heating bed that has like clamps maybe attached to it and a way to like level the salt properly, and that would just improve our processes as a whole. So
Scientific judgment. A lot of real world stuff. And you have to back up and try again. I don't know if I would have figured out the salt. The software guy, that's a solution.
yeah.
The idea, I said, you have to highlight this.
Yeah.
So here's the demo of the heating plate actually working. So this is obviously sped up, but in reality, it doesn't take like too much time to happen. And in that time it's heating up, it's not specifically getting harmed, because obviously beyond like the actual heating up part, it needs to take some time beyond that for the components to actually get. So as you can see, some of the parts have already started desoldering. So you're able to move them like fairly quickly. Obviously, this is still sped up, but like,
But imagine if you have to pick off
yeah,
18 parts.
Yeah.
Then the time gets to be constrained.
so as you can see, the parts move fairly easily, quite quickly, actually. Yeah. So up until now, we had Vignesh talking about the vision system and Rishong talking about the pickup tool machine. So now we also have to consider how it all ties in to the actual gantry system. So kind of combining both the vision and the pickup tool mechanism. So here's how the entire thing is wired together. The brain of the 3D printer is the Raspberry Pi, which has clipper on it, allowing for easy access for printer movement. An external laptop is connected to the camera and is kind of the main player in organizing everything. So the computer takes in the camera feed, it runs the inference, it computes the printer coordinates, it also sends the G-code through a Moonraker WebSocket to the 3D printer to actually make it move. On the toolhead, an Arduino Nano handles two of the main pickup tasks. The first one is the BL touch sensor, and second is the vacuum nozzle. These two are instrumental in actually picking up the components and sorting them in the right boxes. So in addition to all of these components, we also had to have a consistent power to the pickup mechanism. So we salvaged a PC power supply unit, which provides 12-volt and 5-volt rails. Each rail has a 2A fuse on the positive side to act as a safeguard. And all of these live on the single perf board, which you can see here over there. So so we also ran into a few issues while kind of putting everything together. The first major issue that we ran into is a latency between the BL touch sensor and the actual stoppage of the downward Z-axis motion. So just to kind of explain how the BL touch kind of plays into the system, as Rashang previously mentioned, we need to find a height for each component in order to actually pick it up. So our solution was to use a touch sensor to figure out that height. So the touch sensor would keep on coming down and down until it detects the height for a component. And once it detects that height, it stores that height into kind of like an array, having an X component, Y component, and Z component, which the 3D printer uses. So the issue was that the BL touch sensor, after it was triggered, the gantry would still continue moving down. That would sometimes damage the BL touch's tip, the trigger. So what would happen is that it would store the wrong values. So in order to fix this, we initially thought that it would be an issue in the USB serial connection. And then later we thought it would be an issue in the Moonraker WebSocket connection as well. But once we tested both of those, we realized that that could not have been the issue. We found out that the issue is actually how Clipper does the motion cue. So how we kind of wanted it is similar to a while loop. So we want to say like while the 3D printer gantry was coming down, while it was coming down, we want to check if the BL touch would be triggered. And that motion in Clipper is very unique because how it works is that each motion, for example, 0.1 millimeter, is cued at a single time. And all of that is cued in a long cue. So even after the BL touch is triggered and the cue motion stops, it still has to finish the cue before it actually goes in to the stoppage. So after figuring this out, we kind of realized that we needed to space out the downward motion. So we fixed it into 2 different stages. The first stage would be a faster stage until it is around 32 millimeters above the PCB. So that stage would be moving at 0.5 millimeters per move at 300 millimeters per minute. And the second stage would be the more accurate one, which would give a more reliable sense of the height for the component on the PCB. And that stage would be moving at 0.1 millimeters at 150 millimeters per minute. So the BL touch latency was the first issue. The second issue was in the actual hardware part of picking up a component and dropping it in the right sorting box. So the way that we wanted to pick up the component was through a vacuum nozzle. This vacuum nozzle would kind of create like a vacuum between the pump and the component. So that would result in a fixed vacuum that we thought would just drop into the box. But what ended up happening is that vacuum was extremely strong. So that was much stronger than what we wanted to have. So we initially thought that a good fix would be to reduce the surface area of the nozzle, because if it had a smaller surface area, then there would be a lesser residual vacuum force, which means that it would perhaps drop earlier through gravity. But this did not work as we wanted to. So even though we made the surface area of the vacuum nozzle smaller, it didn't drop in the amount of time that we wanted to. So we wanted to guarantee that we get the dropping accurate every time.
So what we did was we created a change in the workflow where instead of simply hovering over the box that we would sort it into, we brought the z-axis down and banged against the side of the sorting box. So even though it would take a little bit of extra time, it ensured a near 100% accuracy in picking up the component and dropping it in the correct box. So here, so essentially, we have a box and it has like kind of rims on the side. So our first idea was kind of hovering over the box, and we kind of hoped that the nozzle would not be strong enough to hold it, and it would just simply drop because of gravity. But our issue was that the residual vacuum force that was kind of holding the component was really strong. So we needed a way to kind of stop that. We wanted to drop it into the box. So what we did was instead of just hovering over, we came down, we tapped the side of the bin so that the component would, so we would ensure that the component would fall into the box.
Just that suction couldn't.
Yeah, there was no other way. It could only suck air out. So let's just go through a quick cycle of how everything kind of ties in together. So step 0, which we kind of saw earlier, was the desoldering of the PCB that Rashang showed. So with that, all the components on the circuit board would be desoldered. So they will be easy to move. Step 1 is to home all the axes. This is an especially important part because in the homing position of like 0, 0, 0, there'll be a reliable place where the camera could see the circuit board every time. Step 2, we need to capture the image for the inference model. Step 3 is to detect the component classes. Step 4 is to map the pixel coordinates to the printer coordinates. Step 5 is to probe the heights of every component to get that X, Y, and Z coordinate system. And once that was done for all the components, to kind of create like a long array for every component, then it would pick up every component with a vacuum, move to the sorting box, and drop it by tapping the side of the bin. And this process would loop until the board is kind of clear of the components that we wanted to get.
Was there any like value? If there was 20 things in the board that you run out.
We kind of implemented that because at the beginning we wanted to ensure that we get the capacitors and then the IC. Those we kind of highlighted those as the most important ones. So we have a demo video for you to see, and in that we show how we get the capacitors and ICs in that.
So one thing I want to add to that is like definitely in the future, if an individual wants to add more capability to the system, like I only want to pick up capacitors for some reason, I only want to pick up ICs, that could very easily be done by just selecting it in the software and sugar.
Yeah, so it's pretty customizable. It's not like hard set to get a certain component. You can switch around easily. So here we have a live demo of the system. Yes. Let me just restart. Oh, sorry. So right there, you can see it probing the first oscillating capacitor. And then it probes the integrated circuit for the height. Yes. Sure that it was all in. So okay, yeah. So sometimes like our thoughts obviously at a smaller surface area.
Vacuum is strong enough such that it won't fall off before it gets the box. But yeah, it could fall off earlier.
So that was a full demo of kind of everything that happens after you desolder the PCB. So now let's talk about how it performs. So as Vignesh previously mentioned, it has a 86% detection rate for mean average precision, 79% classification on the real test board, and a 95% pickup rate after after it taps the bin and drops it into the right sorting box. The pixel to printer coordinate transform has a accuracy of around 0.89 millimeters, and our throughput component rate is 6 components per minute. Although it's not at like one of the extremely high end versions of a disassembly machine, it is a pretty competitive and a pretty fast metric for our component rate. Finally, we have our total cost coming in at $345, which Vignesh said was around a third of our initial budget.
So yeah, obviously, this project, when we came into it, it was under the constraint of having a working prototype by the time we get to the Synopsys Science Fair. So that was about what, a 5 to 6 month window, which wasn't enough to fully flesh out our idea. So if we want to like fully flesh out the idea, our first step is to get a consistently working gripper. So as you may have noticed in like the first demos of the system, I talked about a gripper, but there's not actually a gripper on the system. So when we were constructing the gripper system, we weren't able to get a consistently working prototype because it required some like other forms of materials, because this tip for the suction is,
You hold it in front of the camera.
Oh, sorry, sorry.
Just
this tip for the suction is obviously made out of silicon. So it doesn't care about the heat of the PCBs, which it's picking up, right? But for a gripper, if I wanted to like 3D print something, it would obviously melt when it goes to pick up a component. Because even though they aren't like the components aren't heated up to the point that they're dead, they'll still be extremely hot because it's 240 degrees Celsius. So what we had to prioritize other things, so we weren't able to construct a gripper system that would work in time for the competition. So that's why the demo was also only the suction. So another thing we wanted to do with the gripper was have a bidirectionally rotating gripper. So obviously not all the parts on a PCB are the same way, are on the same orientation. Like you could have a connector this way and another connector this way. So you have a gripper that can only move this way, then it can't pick up all the components, obviously. So that's another thing. Another thing we wanted to do was, as I said at the start, we tried to do a laser-based sensing. We didn't actually like work on it, but we did some research into the type of components we could use, and none of them turned out to be cost effective. But getting a sensing system that worked without contact would greatly decrease our time compared to the BL touch sensor, which is obviously a net benefit for small businesses that want to maximize profitability and get through as many PCBs as possible. So we would like to look further into a laser-based system and like an optical system that's able to just like look over the board and detect the heights. But as of now, we haven't found anything that has the precision or the size constraint and cost constraint that we need. Another thing we wanted to do is create a custom heating plate. So the current heating plate is straight off the shelf, so it has no connectivity to the rest of our system. So if we wanted to run the whole thing, we would have to manually press start to heat up to 240 degrees Celsius, then lower the temperature back to 200 degrees Celsius by hand. So in the future, we would like to construct our own heating plate, which uses a microcontroller to talk to the rest of the system. So the computer vision can say, okay, let me start the heating plate. The heating plate heats up to 240 degrees Celsius, then cools back down to 200 degrees Celsius. Then the system can say, okay, we can start the process, and it all goes up. Yeah. You can lower it, yeah, relatively quickly.
Could you repeat the question, please?
Oh, sorry. He asked if lowering the temperature of the PCB heating plate is like a linear curve, and if it like cools down fast enough compared to like just moving it to a different plate. So I mean, moving it to a different plate is possible, but would obviously require more work. Yeah. Uh, but usually what I've found while the printing bed is moving is, for one thing, it doesn't move that fast because PCBs on our current system, it's a 100 millimeter by 100 millimeter bed. So to move it, there's not too much jerk. But the other thing is that the solder itself, its surface tension keeps a lot of the smaller components that are likely to move pretty still. And for the larger components, even if they move a little, if they're larger in surface area, the centroid won't move so much that the thing will be an issue. But that's another, that talks about another thing I want to improve in the future. And that would be, it's number 7 here, but I'll just skip to it. It's a core XY gantry instead of a Cartesian gantry. So our current system uses what's called a Cartesian gantry, which let me show it here. So this is a Cartesian gantry. And what a Cartesian gantry does is it moves the printing bed itself, like the bed where the items would typically be 3D printed on, forward and backward. Then it moves the gantry and the nozzle. It would typically be a nozzle on a 3D printer, up and down using linear rods, and then we move it left and right with belts. The issue with the system is it's quite out of date. Like most modern 3D printers don't use Cartesian systems anymore. If they want to prioritize speeds, they use something called a core XY system, which only moves the printing bed up and down and then allocates X and Y movement to the extruder. So it would be like a box, and the extruder would move front and back and then left and right, and the heating bed would only move up and down. And the thing with this system is it greatly improves speed. So if anybody's heard of like Bamboo Labs, the 3D printer company, their printers can print up to like 400, 500 millimeters a second, or millimeters a minute. Whereas this 3D printer, I'm pretty sure it only goes up to like 100 at best. So it's extremely slow. But also, as you,
6,000.
yeah, of course. Yeah. And another thing is, obviously, as you said, if the print bed moves forward and backwards, even though I feel like there's a low chance, there's still a possibility of parts moving. So if it only moves up and down, then that eliminates completely the chance of it moving from left to right, because up and down won't cause that issue. So that's one of the major fixes we want to do for the system. Another change we want to do is have a larger heating bed. Right now it's only 100 millimeters by 100 millimeters, but if we want to like have larger PCBs that we want to heat up, obviously we should have a larger bed and have a print bed that has the ability to do so. And then on the vision side, we want to broaden our data set. So we want and broaden our vision system. So possibly improve on the camera within a budget. So like still within $1,000, maybe improve the camera system. And then also diversify our data set. So Greg actually brought this up on our science fair day. So he asked if our system could differentiate between individual ICs, because some companies might want to focus on a certain IC that would bring more profit to them. So we want to diversify our data set and possibly like collect that data that might allow us to differentiate between individual integrated circuits that might bring the most value. So you could just put in a PCB, say, I want these list of integrated circuits or these lists of parts, and it could just pick them up and sort them for you specifically. So we want to like diversify the system so it brings more profit. And then along with the Core XY gantry, another thing, this is probably more in the future, but to improve speed even further, a few like modern like 3D printers have dual tool heads moving on two rails at the same time. So this would be quite an engineering challenge. But if you had two of those systems moving simultaneously, then that would allow you to pick up two components at the same time. But obviously there are some issues, like you have to avoid collision between the two, which would mean mapping out which gets which. And obviously that's a lot more work, but it's still a thought to have in the future to improve the system. So like these are all the improvements we would like to go through to improve the system to maybe make a commercial device or a device that can actually be used by somebody.
So the vision model that we developed is actually available at this website that we made. And there you can find some more information about the technicalities of the dataset production and other and exploring the pipeline there. So you can try it out yourself at that link.
Yeah, so we're also trying to give a quick demo of the website right now.
I have a few sample images on the website to try. Can run the model on it to output the inferences of the position on the board and annotation types.
Yeah, so you can also try this yourself on your own devices as well. We have, I believe we have 3 sample images, and this just kind of gives you how, like a look at how we do it and how we calculate the centroid of
It's called backend.
everything.
Or
Cool.
It's not collab. We just run the .pt file through the website. Yeah. The collab was just to like develop the for the training. So here you can see the annotations. There's the purple is or the pink is IC, the purple is switches, and obviously this is kind of busy to a human viewer, but the computer will be able to understand it, as Greg mentioned previously.
And you can also compare it to how the PCB looked originally. So you can see the mapping. So obviously it identifies those as connectors. The ICs, obviously, as he said, it's very messy. But yeah, you can see the comparison here, and you could upload images of your own if you want to try it out yourself. So yeah.
Is this because that's the one. The size limitation of just checking it out.
No, it'll just be limited to how large the camera frame can capture.
Resolution. So
Yeah, also resolution.
Yeah, higher the resolution, the better.
that would be it. Thank
Yeah,
you for listening to our talk.
Thank you so much for giving us this opportunity to present.
Questions from the audience, comments, feedback?
I want to go over the camera.
So essentially we have a,
Repeat the
Oh.
question.
Yeah, like the camera, connecting for camera.
yeah, so right now we're talking about correcting for camera distortion and how we manage to convert the pixel coordinates into the coordinates that the printer can understand. Is that right? Okay, so what we use is we use a polynomial fit. So kind of we transformed the like the printer bed area into a kind of graph where we have points where we can reference to in each in that grid area. So sorry?
You knew some ground,
Yes,
some factual.
yes. So that's why yeah. Sorry, missed that. Right there. So you can see we have 0.1 all the way to 0.20, and we have those hard set into the polynomial script. So based on that, we can kind of define where like points in the middle are. So using those as like the reference points, as you said, that's how we did it.
It's a supervised learning problem. So
Ah,
they have
okay,
their
okay.
points. Should be. There's the points that the sensor reports. There's the gap. And then what they're doing is they're training the system to minimize the gap, minimize the.
So instead of correcting the for bit plot.
Yeah, we
They're adjusting.
A translates to A prime, B translates.
yeah, we wanted to account for that distortion. Instead of just eliminating it, we kind of embraced it.
Teacher, any comments for you working with them as a project?
Yes.
I've been judging science fairs for 10, 12 years, but I haven't talked to too many teachers, so.
The three of them came to me in September last year. Start with, I mean, I absolutely knew nothing. First, what this is. Here's the. And so at the very end, we actually ran out of time because we're very busy kids, and so we gave them a hard deadline. If you guys want to participate in science fair, you have to have the done by, say, like late January, right? But they were so close. There was so much more to do, and I made an exception because I felt like I was very excited. I saw there was progress. They needed more time, and I always tell my students, yeah.
Can we do something so we can hear what the audience is saying?
Can you pass her the microphone?
Yes.
Maybe go up to the podium.
We need to repeat anything?
Just
I just
explain you're going through the process.
Sure. As their science fair teacher, as their science fair mentor, they came to me beginning the school year with this idea. And as I was just saying, they were very busy students. So I set a really hard deadline of late January. They had to be finished with the project, and that's it. No more time to work on it because the science fair is like early March. But during the process, my goal with my students is because I don't know very much about most topics, is for them to be able to teach me and make me understand. So during the process, I learned more and more and more about their project. So by the end of January, okay, time was up, but I was so excited because I saw so much potential if they had more time. So as I was saying, I always tell my students, if you had $1 billion and all the time in the world, you could probably make this work. But we don't have that kind of time. So we stretched the deadline, right? And I said, okay, guys, I'm going to close my eyes and I trust you. You have 1 month, you have a month and a half before the science fair, and you just got to do it because I think this has so much potential. And we did. They did lots of things, and I was most excited about the salt. I was like, oh, I was really excited about salt because students get really, they want everything to be fancy and they want everything to be really scientific and everything. And they don't realize that sometimes the most important engineering solutions are simple ones. And if you can find simple, very cost-effective solutions, that's like the best thing in the world, right? So that I was really excited about that. And actually, initially, you weren't going to talk about that much. You had it sort of in the corner,
Yeah.
right? And I was like, no, you have to really talk about this point. So I'm glad that you also reinforced that for them.
Yes.
There was a question from the chat,
I can-
which says, how well does the system distinguish R and C, which I guess means resistors and capacitors, given that they look very similar, especially in the 042 and 0603 sizes.
I'm not familiar with the specific sizing standard that you named, but just to talk about the general ability to distinguish between smaller parts. At the current moment, the data sets that we used were mainly focused on large components because our project was initially and always probably not going to be precise enough to pick apart these extremely small like test points and resistors and such. So our data set wasn't sufficiently equipped to handle such smaller components. But our future goals is to get maybe a more industry standard level data set with smaller components and higher quality annotations and such, so we can improve on that in the future.
Or even get into some semi-supervised learning approach.
Yeah.
Where you're labeling some of the data in a model to try and give wrong labels that could just.
But another thing for that is that for our like current goal, you really don't need to see the smaller resistors and capacitors because I mean obviously our
What's the value?
yeah. So I mean yeah, these are like usually dirt cheap. And even for like normal capacitors or like inductors, you don't really need them for profitability. We just thought for our project they might be of use for somebody, let's say in a small business that's working with computers every day. Let's say they need a part. But usually for these like extremely small parts, they usually have rolls of them. So they don't really need them. Yeah, yeah. Yeah. Yeah.
Please repeat the questions.
He was talking about how the smaller resistors usually get recycled for materials. So they're like for materials are more valuable for recycling. So they usually get recycled. Like inductors and capacitors are usually more valuable for getting recycled just as their raw materials. So he was just talking about that to as a response to what I was saying.
And we do classify those. You could try it out on the website, but we have inductors, capacitors. Especially if the image is very like if it's close up, high resolution, then it's extremely accurate. It's not extreme. It is pretty accurate at even getting those smaller components. On our gantry setup, the distance between the PCB and the camera was around 489 millimeters. So it was a pretty big gap. And if we reduce that gap, then the detection would also be extremely accurate.
But yeah, as I was saying before, the real reason why our project looked at, I mean, realistically, if you're looking at pure profitability from raw components without scrapping them for their materials, you're only focusing on integrated circuits, basically, because those are the ones that some of them can be extremely valuable, some of them might be somewhat valuable. But we just, for the sake of our project, we just spread it out. Because, I mean, somebody at a small business could use an inductor, they could use a capacitor if they wanted to use it in something else. But like on a pure profitability perspective, obviously only the integrated circuits matter. So yeah.
Well, I'm going home and trying. Definitely, I'm looking for.
Thank you.
Could you repeat what the audience is saying?
He said that he was going to go home and try heated salt on his PCB to see how well it works in like desoldering the components. Yeah.
Another question. Accurately measure.
The question he asked was, how do you accurately measure the temperature? And for this project, we didn't have any temperature measuring software other than what the screen on the device showed. But in the future, as you were talking about earlier with like the temperature curves and all, I want to account for that better. So like for this, we didn't like ensure that the components weren't being damaged. We just had like a rough guess that if the temperatures were around here in this time frame, they wouldn't get damaged. But in the future, obviously, we can't just guess, right? And we can't just predict because this is profits at stake. So when like I mentioned before that we would like to design our own heating plate to tie into the system. I would probably like to have a more detailed temperature graph that like some of these newer soldering irons, they show like temperature curves when the soldering iron is cooling down or heating up. So I'd like to integrate that into these heating plates.
I can't.
Yeah.
Don't count the phone as part of it because everybody carries around.
Yeah.
a phone. But you can just put the infrared camera on that.
Yeah.
I can get 20 by 200.
He was just saying that you could get an IR camera that connects to your phone pretty easily and look at the temperature that way, and that wouldn't be too costly for people. So yeah, that's also an approach we could use. And maybe we could also think about, like, as you were saying, the time it takes to cool down is also something to take into consideration. So the heating plate switching is maybe something we could think about, or maybe like having like modules that could actively heat and actively cool the plate faster would also be a consideration. But I'm not currently sure how we would go about that. So that's also a possibility.
As a thought, you might look into the thermal conductivity result, see if there's something that conducts heat faster, because if your plate cools faster, you don't want something that retains heat.
Yeah.
You want something that'll cool when the plate cools.
Yeah.
So that way you avoid overheating your circuits.
Yeah,
as a suggestion.
Yeah, we're yet to test out different kinds of those conductors, but that is definitely one of our future plans.
Whatever your power.
Yeah.
Yes.
He was just saying that we would have to test how well the salt conducts heat. So even though like the heating plate says it's cooling down, that doesn't necessarily mean the salt has cooled down completely. So we would have to check how the salt cools down with the heating plate, and if we could use a more suitable material that heats up and cools down a bit quicker than the salt for something like that.
Have you thought about using heating oils?
The question was, have we thought about using heating oils? And I don't
Sorry,
think
not heating oils, but oil.
So as like to replace the salt, is that what you're saying?
no, I've not actually looked into that, but could you explain more?
Because the temperature.
Okay.
Yeah, that's definitely. future
Yeah, that's
direction.
definitely, so he was talking
Yeah.
about if you could use oils that could be heated up because their temperature can be controlled well, and obviously they don't conduct too, so they're fine to be used. So yeah, that's definitely something we'll take into consideration. I didn't look into that for the project, but that's definitely a possibility. Yeah. Thank you.
Solder.
Question about software aspect. So the future. In the rapidly developing field of AI, how do you envision incorporating, new models or new AI systems into the software?
So the question was how, with the rapid development of AI in the future, how do you plan to streamline some of the processes that we have going on in the project? So recently, not recently, like previously, he mentioned about like getting key specific types of ICs from like different companies that you could harvest from, and I was thinking theoretically we could use like a text-based detector that would detect like key text from certain models or certain models of ICs that would be able to get like specific brands or specific types of ICs to extract more profit. I mean, they're also like, I think that is one of the solutions. I mean, I haven't specifically thought about how future technologies could help us in some of those other aspects, but that's like an idea that I had. Yeah, I think that would be, yeah. So.
Question about training data. So did you do any image augmentation for the images, or you just using?
Yeah, we
Repeat.
Okay. The question was, did we modify the image size? So did we augment the image size in the training data set to train on? And we normalized all the images to a 640 by 640 image size for the model to train on. So we did change some of the images there, but if in the future we would maybe use a higher resolution image size so that the model can detect more accurately on each component. And also, but the reason why we didn't opt for that is because of time constraints and also processing power. We didn't, the Colab A100 GPU that we're using would take much too long to train on it, and also would take a longer time to also process the image in subsequent attempts. So yeah.
Yeah, I was thinking less of the image size, but more the image, because that will help you increase the
Yeah.
size of things.
Yeah, that's, I actually considered doing that later on, but the so the rotating, yeah, that would definitely be a possibility that we'd consider in the future. I did some of that with like augmenting certain image, certain component types to more accurately train that, but yeah, that would definitely be something that we could implement in the future.
Yeah, I'd just like to give an example of Vignesh, what Vignesh was talking about. So in our testing, we found, we were looking at a few capacitors, and some of them worked better when they had like a little bit of gray on top and like black on the bottom. And if we kind of normalize that, that would definitely improve the accuracy of the system. So we will definitely want to implement that.
Yeah, and we also saw that like boards with, if it was rotated like 30 degrees or 45 degrees, it wouldn't detect nearly as accurately as when it was like straight like 90 degrees on each plane. So yeah, we definitely want to improve that in the future.
Yeah, that you can improve with the image rotation, because you have training sets with different rotations.
Yeah. Yeah, so Greg just said that you could with using image augmentation, you could modify the data set to have more rotations of each of the image, so that when you actually rotate it for testing in real life, you would be able to recognize more accurately on those cases.
Well, I think we're done for the day. A round of applause for our speakers again. Thank you.
Thank you.
So Bill, you can stop your recording. Thank you for your help, Bill.
Okay.
So feel free to visit with our speakers if you have other questions, or family members, or a teacher. You can disconnect. If we have any leftover food, you're welcome to take things home.